Okay, let's move on to question 2. So this is practice exam 2. For your response, question number 2. Here's the picture. So interesting. So it says a student holding a stone of mass m at rest at a height h equals hc, so right there, above the surface of a deep pool of water is shown. Student drops the stone. Resistive forces as the stone falls in the air are negligible. As the stone falls through the water exerts a resistive force. Okay, so there's drag in the water, there's no drag in the air. There's the water down there. There's drag in the water, there's no drag in the air. Magnitude of the force in the water exerted on the stone is, force of water is B plus kV. B and K are positive constants. I think it should say, and V. V is the speed of the stone. Okay, so that's pretty common resistive force, a linear resistive force. So I'm expecting some sort of differential equation coming up, right? Okay, the following times describes the motion. So T2, T equals 0, it's at rest. T1, it's at this height. T2, it's hitting the water. Traveling with speed V2. So we're just going to say V2 right there. V2 is greater than the velocity, the terminal velocity of the water. Okay, so it's going fast. It's going to slow down when it hits the water because it's going faster than the terminal velocity. T3, the stone reaches terminal velocity in the water. So somewhere down here, we're just going at a constant speed. Constant speed in the water. Okay, let's move over to what the questions are. Let's see here. They're often going to have you draw some free body diagrams. So as expected, here we go. The dots represent the stone at times T1, in between T2 and T3, and at T3. On each draw and label the forces, not the components, and so on. Each force must be represented by an arrow. You have to make them the right length. So at T1, that is when it's halfway down. So all we have at T1 is going to be gravity. So I'm just going to draw an arrow like this, and I'm going to label it FG. That's it. There's no air resistance in the air. Between T2 and T3, so T2 it hits the water, and T3 it's at terminal velocity in the water. So it's going to be slowing down, which means we need an upward acceleration. So I still have to have mg going down, or FG. So now looking back over here, I probably should have made this FG shorter because I need my water bigger than FG. But that's okay, I'm just going to make it go above here and label it FW. So you need to make sure that this force is bigger than this force. So that's fine. And then my FG should stay the same for all three of them because they're the same, it's the same rock and gravity is not going to change. And then when it's going terminal velocity, we know we have balanced forces again. So there's FG, and then there's force of water, just like that. Okay, that's pretty easy. Oh boy, here it comes. Part B, derive an expression for the speed v of the stone as a function of time for times greater than t2. Express your answer only in terms of these given things, the height and so forth, and physical constants. Begin your derivation by writing a fundamental physics principle or an equation from the reference sheet. So I will say I did this in advance, and this is a real bear of a differential equation problem. And I talked to other AP physics teachers, and they agreed that solving this differential equation is more than they usually ask for on an AP test. So I'm going to set up the differential equation for you, but I'm not going to solve it all the way. And you're going to see it's not that hard. It's just more than you'd really be asked to do. Usually, my sense is that they're only going to ask you to write the differential equation. So let's come back over here just so I have some space. I guess I'll try to work in this space over here. So what's happening here? We're going to start with our fundamental physics principle, which I'm just going to write as F net equals ma. This is a forces problem. Whenever you see drag and you have a formula for force, it's a forces problem. And sort of one of our least favorite places to go. I'd rather do energy and momentum, but forces is going to be fine. So F net equals ma. And we're talking about the scenario here where we have it hasn't reached terminal velocity yet. I guess it could have reached terminal velocity. It's just greater than T2, times greater than T2. So these are my forces. I'm going to choose up as positive, I suppose, because I know my acceleration is in the positive direction because we know it's slowing down. So it doesn't really matter. So I'm going to come over here and I'm going to say FW minus mg equals ma. Good. And now FW is given up here as this. So I can write B plus KV minus mg equals ma. And then they're going to want it to be a differential equation. So I'm going to put my a as a dv dt. B plus kv minus mg equals m dv dt. And then really they're going to want you to separate out the dv and the v part and try to get those together. So I'm just going to divide my m over to the other side, and I'll just write it as dv dt equals this stuff, b plus kv minus mg over m. So I just took that m and divided it to the other side. And then I'm going to take this stuff over here and take this dt to the top, just to set it up as a differential equation. dv over b plus kv minus mg equals dt over m. Now, they want you to, in this particular problem, go ahead and solve this, which is a little bit of a pain because we're going to need to take integrals. It's not that big of a deal. So we're going to integrate this side from t2 to some other time t. And we're going to integrate this side over here. When it hits the water, it's going v2. Remember that. So we're going to go from v2 to some other speed v over here. So those are limits of integration. Now, one of the other issues in this problem is that v2 is not one of the things we're supposed to have in here. So there's a little bit of a side quest for this problem in figuring out what is v2 in terms of other things. So then they want you to side quest over here to figure out v2 in terms of this other stuff. Well, this is a conservation of energy thing. mgh is 1/2 mv squared. And if you can just remember this, that v is square root of 2gh in these problems, that'll tell you how fast something's going once it's dropped a particular thing. So v2 is going to be the square root of 2ghc, which was the starting height right there. So I would actually have to put this in for my integration way down there. I guess I would probably do the integral just having v2 in there, but eventually I'd have to stick something else in there, which is a pain. This is going to be a natural log. This one's easy because it's just integrating dt, and then you pull the 1 over m out. But this is a natural log, and you've got your limits of integration. And so I would say if you got to the test, if you're like super strong in calculus, it's just like your thing, and you love calculus, go for it. If you're like, it's probably only, we can look at the scoring guideline, but it's probably only worth an extra point to actually solve this thing. So I would say leave it like that and be like, I don't know. I just can't imagine they're going to ask you to do a differential equation that looks like this. It's not that hard. It's just a pain. There's a bunch of steps to get it to look nice. And I think if I looked at the answer doesn't even look nice. So we're just going to call it quits there. And that's totally fine. So now let's go over to part C. So part C says on the axes in figure 3, let's look at the axes over here. Bring those up. So there's the axes. Scooch this up. On the axes in figure 3, sketch a graph of h as a function of t. So the height as a function of the time. Okay, so that's reasonably easy to do. It's just just pull this into here. It's just a position graph, right? So we can know how to draw position graphs. That's like a really easy thing to do. So the first part's actually really easy because we know it's accelerating. And it's accelerating down this way, and it's coming from, so I would start out here and maybe make HC right there. And then we know it's going to get to 0 here. So that's cool. And we just have to remember what's the shape of a graph of something that's accelerating, and it's going to be a parabola, and it's going to be a parabola this way. Oops. So we're starting right there, and we're getting faster and faster and faster as we go down. So that's pretty easy. Now this time between T2 and T3, that's the time when it's in the water and it's slowing down, but it hasn't reached terminal velocity yet. Let's just quickly think about what's going to happen after T3. After T3, it's going at a terminal velocity, so it's going to have a straight line over here, a straight line going down. So we need to bridge from here to there, and it's going to have a straight line going down over here. So this part's still going to be curvy, it's still accelerating, but this time the acceleration is going to be up because it's slowing down. So I'm just going to kind of smoothly draw something like that. It's not going to stop though, so I don't want to take this part in here and make it curve all the way like that because it's not going to stop. So I just wanted to curve a little bit, and then I want to maintain whatever slope was here. I just want to keep that slope going down just like that. So there you go. Not so hard to do. Let's look at D. Consider the case where the student drops a second stone of the same size and shape but greater mass from the same height. The values of B and, oh, I think there's supposed to be a V in there again. Values of B and probably K. Look back up here. So it's this thing. It's probably K again. So the values of B and K are this unchanged. Let's get this up. Describe how one feature of the sketch drawn in part C would change in this case. Justify your answer. Justification may exclude impression. Okay, must include conceptual reasoning. Okay, so what's going to change on here? This part shouldn't really change too much because there's no air resistance and it doesn't really matter what the mass is. So in here, it's going to change a little bit. And something to remember about drag is that since the drag force is just part of the velocity, the mass is not going to change the drag force. But the mass is going to change the gravity force. So in that middle section right here, where it's still slowing down, we've got this and this. I'll just write it as mg. Let me scooch that up a little bit. So this is this middle section right in here. And then this is going to stay the same because we hit the water with the same speed. So this is going to stay the same, but this is going to increase a little bit. It's not going to get bigger than this right away. It's never going to get bigger than this. But what I would say for this is that this shape is going to be less acceleration down in here because the gravity is going to be, the difference between these two is going to be less. And then the other thing we can maybe say is that this terminal velocity is going to be a little bit less because objects that have bigger mass but that are the same size, this terminal velocity is going to be a bit more. Sorry about that. So the terminal velocity is going to be more because we have the same size and shape but a greater mass. So if you have the same size and shape, then your resistive force is going to be the same relatively, but you're going to have bigger gravity force on it. So you have a bigger terminal velocity with a bigger mass. So if all things being equal, if you had two skydivers that were the same size and shape, and one of them was more massive than the other, the more massive one, let's say this had a big M and this had a small m, the more massive one is going to have a higher terminal velocity. So that's that. Okay, so that is question 2. And then of course we'll move on to question 3.